Hi, everybody, and welcome to our second webinar this month, February. This is Dan Barry in Silver Spring, Maryland, and thanks for joining today. We're going to have a webinar on the topic of cloud modeling and climate and Earth system models. This is expanding a little bit on a theme from a webinar we held 2 weeks ago on the topic of weather and climate. In a talk that was given by Chris Bretherton, he spoke a little bit about some efforts that he's leading in a climate process team to improve the representation of clouds in NOAA models, both at GFDL and also in the operational modeling suite at NCEP. And we're going to expand a bit on that particular talk, and we'll hear from 3 speakers today. We're going to hear first from Chris Golaz, who's at NOAA GFDL. Chris is a member of Chris Bretherton's climate process team, and he's going to talk a little bit about efforts related to that climate process team at GFDL and also some of the broader efforts at GFDL for cloud parameterizations and other atmospheric parameterizations related to better simulating clouds. We'll hear second from Steve Krueger, who's at the University of Utah, and Steve is leading a second climate process team that's funded by the CPO MAPP program, and he's going to talk about cloud-related parameterizations that they've developed and that they're now working to implement in the operational modeling systems at NCEP. And then third, we're going to hear from Roger Marchand from University of Washington, and he's going to talk about efforts that he's been working on over the last few years funded by MAPP that are related to embedding cloud-resolving models in climate models. And he's also going to talk a little bit about using adaptive grids in global models, which basically enables increasing the resolution dynamically in the model when it's needed to represent some high resolution or small scale features as required by the meteorology. So the format, will have these 3 talks, and in between the talks, hopefully we'll have some time for questions. I've asked Steve, Chris, and Roger to keep their talks to 15 minutes. And I also have these slides circling around right now where I've given a tip on this slide right here about how to ask questions if you're logged in remotely. So it's pretty simple. You should see a banner at the top of your screen that says Viewing CPO Mains Desktop. If you hover your cursor over that, you'll see a participants list. If you click that, a participants window will open up, and in that window on the bottom left-hand corner, you can raise your hand. Once you do that, we'll be able to see that you have a question, and I'll unmute your line. So please feel free to raise your hand as you have a question pop up during the talk, and then at the end of each of the talks, we'll take some time for questions and discussion. So first up is Chris, and Chris, are you on the line? Chris, are you there? We're not hearing anything from GFDL at the moment. Are you guys there? Okay, we're still not hearing anything from you guys. I'll wait a couple more seconds. I know we had some issues with the audio while we were setting this up. Okay, so I'm going to give Chris and the GFDL people some time to figure out the audio on their end. And I think in the interim, we'll move on to our second scheduled talk, which is from Steve Krueger. Steve, are you on the line?
Yes.
Can you pinch hit?
Can I do what?
Can you pinch hit? Can you talk? Can you
Sure.
give your talk first? We're having trouble hearing from GFDL, so. Okay, so Steve, I just transferred control over to your computer, so just share your desktop with us and bring your slides up full screen.
Okay.
Steve, we're not seeing your screen yet.
Well, do I have to do anything?
Yeah, you have to share your desktop with us again.
All right, I have to find that. No, there it is. All right. Okay, how about now?
Yeah, it looks good. So whenever you're ready, take it away.
Okay. Okay, well, what we've been doing is working on a PDF-based turbulence closure model, and I'll go through and review the basis of this and give you a little bit of an idea of what we're doing at NCEP. So that project has just started, so I decided to focus this talk on really the foundations of this approach. So as you all know, in a climate model, we have limited resolution. These days, it can go down to below 100 kilometers, but certainly in no way can we reach down to the large-eddy simulation scale, unless perhaps if we have an embedded LES, which Roger will be talking about. So one approach that has been used is the Multiscale Modeling Framework, in which a cloud resolving model is embedded in a GCM, but the cloud resolving model is still of limited resolution with a grid size and order of 4 kilometers. So we're still left with the problem of parameterizing small cumulus clouds and turbulence. We can use large-eddy simulation models to develop parameterizations for these other models, and that's part of what we've been doing, is using the LES approach as a test bed. Okay, and then here's a slide. I'm sure Roger will show this later, showing the idea of embedding a two-dimensional cloud resolving model in a GCM, and then we have this problem of still parameterizing the turbulence. So this has been a lot of the motivation for our development of what we call SHOC. Of course, we all know that boundary layer clouds are important, and if we have a model that can only resolve the large clouds, such as a multi-scale modeling framework or any sort of coarse grid cloud resolving model, we're going to be leaving all these small clouds unresolved. So one approach for better representing these clouds and turbulence is the assumed PDF method. Chris Golaz's name is going to be coming up when I describe this in more detail. He's one of the originators of this method. The method parameterizes subgrid-scale clouds in a unified way. Notice clouds and turbulence. It was initially developed for boundary layer clouds and turbulence. It can be extended to all types of clouds, and it's a very promising method for use in coarse grid cloud resolving models. Again, this is what its initial development was for. So this is a slide which Chris Golaz would recognize. This is borrowed from a talk way back when he was working with Bill Cotton. The assumed PDF method contains 3 main steps that must be carried out for each grid box and time step. First, we need to predict the means and various higher order moments, and perhaps we don't need to predict the higher order moments. We can perhaps diagnose them. Once we have estimates of these moments, they allow us to select a particular PDF from the assumed functional form. And what that functional form is a very important aspect of this approach. Then we use that selected and specific PDF to compute higher order terms that may be used, and we use it to calculate things that we need to estimate the turbulent kinetic energy and the cloud fraction, cloud liquid water, so on. So it ties together the turbulence and the cloud scheme. So we follow the approach that Larson and Golaz used, a 3-dimensional PDF, which means 3 variables here: vertical velocity, total water, meaning total suspended water, vapor and liquid, or vapor, liquid, and ice crystals, and also the liquid water potential temperature, which can be generalized in the case of cloud ice. So we have a trivariate PDF. Now, the shape of this PDF is something we'll discuss next. This is a diagram from a simulation, LES, of some shallow cumulus clouds. And we can see that within an area of about 6 by 6 kilometers, we've got a whole array of clouds, and obviously, properties of the clouds. This shows a slice at a particular level, and the color scale here is showing the vertical velocity. So now we can take the vertical velocities at this level and form a PDF. And this is just looking at that cross-section straight down. So here's the PDF, and the red is showing all the grid points, and the blue are showing the cloudy points. And you notice that to first guess, we have a Gaussian distribution, but then when you consider these cloudy points, it's obviously highly skewed. So a Gaussian PDF would not be appropriate. And in fact, this diagram here gives you an estimate of the error that you would get from a Gaussian. So the red points here are approximately Gaussian. If we just include them, then we get these values of cloud fraction, the green, sorry. Then we get these values of cloud fraction, cloud water, and liquid water flux. When we include all the points, including that long tail, then we get the red bars. And you can see there's a huge difference, especially in things like the cloud water and the liquid water flux, which is an important term in the buoyancy flux. So we'd like to use a PDF that is a PDF shape, that is flexible to represent cloud regimes of all types, few percent to overcast, and simple enough to allow analytical integration of the moments over the PDF. So let's just give one more example of what the PDFs look like. This is for a stratocumulus cloud. This is a cross-section. Well, this is one particular plane in the three-dimensional PDF showing the total water and liquid water potential temperature here. This is the line that divides the cloudy points from the clear points. And you can see that for stratocumulus, nearly all the points are in the cloudy region. And you have almost a fairly symmetrical distribution. For shallow cumulus, though, again, we see another tail. This is in theta L, and then in the two-dimensional cross-section of the PDF, we can see this tail extending out. And even though most of the grid points are here, the cloudy points are all within that tail. And so here you see that tail again. So again, just motivating the use of a PDF, which is asymmetric. So we know a single Gaussian isn't going to do. A double delta function has often been used for mass flux type models where you have one delta function for the clouds, another for the environment. But for the types to be more general, we end up using a double Gaussian. And this is the one from Larson, Golaz, and Cotton. And actually they had two types of double Gaussians. We won't go into that detail. Llewellyn and Lowe also proposed a double Gaussian that requires, it's slightly more complicated. So if you're going to specify the actual PDF, you need to have 7 parameters for the double delta function. That includes the 3 means, the 3 variances, and then some covariance. For the single Gaussian, you need 9 parameters. For the double Gaussian, because of some assumptions made, you only need 10, just one more, and the Llewellyn-Lowe needs 12. So let's look at how some of these Gaussians actually fit. The double delta is shown in the arrows here. The single Gaussian is in the blue, and to fit the whole PDF, it has to extend out here a little ways, so it's not a good fit. The Larson-Golaz-Cotton double Gaussian is shown here, and the Llewellyn-Lowe double Gaussian also. So both of the double Gaussians have a better fit. And the real test is not just to look and see how well they fit. It's actually to compute the things that you need from the PDF: cloud fraction, cloud water, liquid water flux. So that's the approach that we've taken, is we've used a number of LESs, including large domain simulations of deep convection, to test this approach. And we're not going to show all the results here. We'll just mention that we've used a number of these cases from GCSS and other field experiments to do tests. How am I doing on time?
You have about 5 minutes.
Okay. So this slide is showing how well the various schemes do as a function of the model horizontal grid size. And what it's showing is the correlation coefficient between the predicted and actual benchmark liquid water mixing ratio. This is just for one particular benchmark LES. And you can see that the single Gaussian here and the double delta function here only perform well when the grid size is quite small. The other ones here, all the ones in blue or green, are the double Gaussians, and they perform well out to large grid sizes. And they do the same for this quantity liquid water flux as well. So certainly we see a benefit of using the more complicated PDFs. As the grid size gets larger, the distribution, the subgrid distribution is just going to get more skewed, especially in cases with cumulus clouds. So what have we done? So far I've basically showed you the methodology. What we decided to do is to simplify the approach, and called Simplified Higher-Order Closure. I don't know if that's an oxymoron or not, but it makes a nice acronym. In our case, the second order moments are diagnosed instead of predicted using simple formulations. And we also diagnose the third moment of vertical velocity, which is a key moment. And then we still predict the subgrid-scale turbulent kinetic energy. All the other moments are functions of that. Okay. And the other thing that we do that's relatively an advance over other previous methods is we adopted some ideas from Texeria and Chenet for the length scale, and we formulated a general length scale that is an improvement upon previous ones, the Bugeaud length scale in particular. And this helps make our scheme general, and in a sense makes up for some of the lack of prognostic moments. So this is a slide that just shows how we predict the moments. I'm going to skip that in the interest of time. And I'm going to skip this one. I just want to show you a couple examples of results. Out of all of our results, we've looked at, I'll just show you the precipitating cumulus case here. So we have comparisons between standard SAM, which doesn't have SHOC in it, and SAM with SHOC. So these are cloud resolving model simulations, with different grid sizes. So these are full-on prognostic tests. The model is run with these grid sizes. And for standard SAM, we get liquid water contents up to 0.25. The LES profile is right here. And SAM SHOC matches the profile very nicely for all of these grid sizes. Notice the scale has changed. This gray line is the same as the gray line here. The maximum value here is just 0.015. We also get a nice agreement for precipitation rate. It collapses. It doesn't have a dependence on grid size as it does for standard SAM. For stratocumulus, this will give motivation for Roger's talk. We do have some difficulty because you do need to have adequate vertical resolution. Here is our benchmark simulation showing cloud fraction over 8 days. Here is standard SAM as in MMF, so it's 2D, has a very coarse, has a delta Z of 150 meters, and this is SAM SHOC. So This is what you get in the current MMF. This is what you get in the MMF if you include the SHOC. And obviously it's an improvement. It doesn't completely agree, but it is better. So the main accomplishments this code has been implemented in the MMF and actually been run for AMIP simulations. We just have some preliminary results. And in the interest of time, I think I should probably skip this, but just say it does improve the representation of low clouds over land. The stratocumulus is, you just need higher resolution. It doesn't decrease the representation, but it doesn't markedly improve it either. So in summary, we've got a diagnostic higher order closure with an assumed double Gaussian joint PDF, a turbulence length scale that depends upon the subgrid-scale TKE and large-eddy length scales. This is new. The diagnostic approach is new. We can represent many boundary layer cloud regimes with little dependence on horizontal grid size, and very importantly, it's economical. And I think that's it.
Great. Thanks a lot, Steve. That was great. So again, questions from those online, please go up to the top, select participants, and then click the raise hand feature. In the meantime, any questions from anybody here in the room for Steve? Hey, Steve, I'm just going to wait and see if anybody raises their hand online.
Okay. I can mention while we're waiting that we are implementing this in the NCEP GFS. We're just 6 months in, and so we do have the code installed. We're currently debugging it, and we'll be going into the testing phase shortly. And Alexei Velachitsky is the one working on that with Murthy, Srinivas Murthy.
Yeah, thanks for giving that update. Do you have any ballpark estimation of when it would be in operations potentially?
Well, that's always dangerous to predict. The typical testing cycle takes, typically 2 years. So we'll start to test it later this year, and then it'll go through a long period of testing and tuning. So late next year might be the earliest that we can see that.
Great. Okay, I haven't seen any hands raised, but I appreciated that information on the NCEP side, testing that in the operational system there. So thanks a lot, Steve. Really appreciate it.
Sure. You're welcome.
Okay, let's see if we got Chris. Chris, are you on the line?
Can you hear me?
Yeah, we can hear you. Great. That's great. You got the audio working. Okay, so Chris, what I'll do is transfer control over to you guys, and I tried this out earlier. Just share your desktop with us. Okay, looks good, Chris. So whenever you're ready, go ahead.
Very good. Thank you. So today I thought I would give you a brief overview of some of the recent development that we have been doing here, working on the next generation climate model that will be AM4 and CM4. Just one slide giving you a very brief overview of some of the history of GFDL climate model. For CM3, we had one main model, which was CM2. And then later on, it was decided by GFDL that it would be more efficient to branch into different directions because GFDL wanted to explore various aspects, including carbon cycle, high-resolution couple model, seasonal forecasting, high-resolution atmosphere for the purpose of tropical cyclone, and then advanced chemistry aerosol, including cloud aerosol interactions. We couldn't do all this in one single model, so it was decided to instead branch into a number of different models. For the next generation, CM4 and ESM4, we're going to try to bring back some of those branches together and try to unify some of the lessons that were learned from those different models into one common model. So this is the model we have been working on for the last 2 years or so, and hopefully it will be finalized maybe sometime this year and one next year. So some of the borderline targets of this model, for CM4, we are targeting a new atmosphere, which is called AM4, and a resolution of ½ degree, with an option to have a lower resolution atmosphere of 1 degree. In the ocean, the new model will be MAPP6 with a target resolution of ¼ degree horizontal resolution. So this is a very substantial increase in resolution going from CM3 to CM4. You see it's a 4 times increase in the horizontal resolution, both in the atmosphere and the ocean. So that means about a 16 times increase in the number of grid points. So that's a very big model compared to what we have been running before. And we hope that we'll have enough computer time to actually run the model fully. In addition to increasing the resolution of the model, we're also working on updating and improving the physics of the atmosphere. And we are looking at a number of different updates that are under consideration for AM4. One line of progress is regarding the convection. Mingjia has developed a new convection, which he calls a double plume convection, an extension of what was used in high RAM, but now with 1 plume for the shallow and 1 plume for the deep. We're also looking at reformulating previous convection that were used in AM3 as also an option. We are doing some work on updating the large-scale cloud scheme. One of the things we are trying to do is move towards a PDF type of cloud scheme, as a little bit in the spirit of what Steve Krueger mentioned earlier, but simpler. We're also looking at updates in the microphysics, the radiation, aerosol, and the boundary layer, not to mention other things on there. I won't go into details of those updates, but the main motivation is to increase the physical realism of the processes while at the same time improving the simulation fidelity. And this is sometimes not as trivial as it should be, or as it may sound like it should be. So the last 2 years, we have been working mostly on the atmosphere side using fixed SST simulation, which we call MAPP. But in the last 3 or 4 months, we have been doing more couple simulation, coupling prototype AM4 atmosphere with prototype MAPP6 configuration. And the results I'll show you today are from one of those prototype couple CM4. This shows the annual precipitation. On the left is the observation from GPCP, and on the right, the models, the previous generation CM3, and one of the CM4 prototypes. So typically, we look at the difference rather than at the actual maps. This is what the difference look like. Red colors are area with excessive precipitation, and green bluish color are area with a lack of precipitation. If you compare CM3 versus CM4, you see that there's an overall substantial improvement. The RMS error goes down from 1.28 to just above 1. The correlation also goes up from 0.81 to 0.9. And you see that CM3, like all CME5 model, was suffering from a double ITCZ, which is characterized here by those excessive precipitation, those red bands here. It is still present in CM4, but it's substantially reduced compared to what it was in CM3. So this is quite a progress that we have made. An area that is more challenging is the Amazon, here and here, and most GFDL, all GFDL models and most CME5 models suffer from a dry bias in that region. That has not improved yet in the CM4 prototype that we currently have. We're hoping to be able to make some progress there, but we have not accomplished that at this point. The double ITCZ is really shows up very strongly if you look at the season of March, April, May. This is the difference plot. You see a very large excessive precipitation in CM3. It is still present in CM4, but it's substantially better with the RMS going from 1.9 to 1.36. So this is progress, incremental progress, but nonetheless substantial progress. We also pay a lot of attention to the clouds. We try to improve the fidelity of the clouds in our models. And one way to look at it is to look at the cloud radiative effect at the top of the atmosphere, and we typically compare that to the CRS EBAF data sets. This is the observation, and again, this shows the difference between the model and the observation. And you see that going from CM3 to CM4, there is also an improvement. The RMS goes down from almost 11 to 9. That's a very substantial improvement. This is not something that is easily achieved. It took us a lot of work to get there. And you see the improvements in the Pacific. You see the biases are still there, but they are reduced. Over the Southern Ocean, you see reduced biases. The Atlantic also has reduced biases compared to CM3. One area where you don't see much changes are in the stratocumulus region, which show up here in those red spots here, meaning that we don't have enough reflection from the stratocumulus clouds. That is a long-standing problem in GFDL model as well as most simplified model. This is a figure showing 20 simplified models from Wang and Frierson 2013, and it indeed shows the shortwave cloud radiative biases, and you can see that those three regions show up very well as positive biases also in the average of 20 simplified models. So the problem is shared by GFDL model and many other models. One way we are trying to address that is by working on the cloud parameterization and the PBL parameterization. So we have an alternate version of AM4 that has a different cloud scheme. This one is based on a PDF representation. And that one works quite well in MAPP mode. It produces a very good simulation with an RMS of around 9. So it produces a very nice simulation in MAPP. And on top of this simulation, we can then change. We have a new version, a new formulation of the PBL scheme, and the PBL and the PDF scheme interact very closely. And if we do that, we actually manage to substantially reduce the bias in the stratocumulus region. As you can see, the bias is still somewhat present of the coast of Peru here, but it's reduced by 3 or 4 contour lines. It's almost gone over California and Namibia. So this is a very promising development. But unfortunately, at this point, this simulation does not couple very well. And even though the MAPP simulation with fixed XST looks very promising when we couple it, it doesn't look very promising today. So we have more work to do, and we don't know yet whether this will be able to be incorporated in CM4 or not. This is some of the challenges of trying to build a big global climate model. Looking now at Longwave cloud radiative effect, which shows more of the high clouds. CM3 had a bias in the tropical region with too much excessive high clouds, and that bias is substantially reduced in CM4. You can see the colors are reduced, the RMS is improved. One thing that we can do with a model at half a degree atmosphere, around 50 kilometer atmosphere, is we can start to have what we call hurricane-like vortices. So we can start to have vortices that look like hurricanes. And this was demonstrated by the previous model, previous high-resolution model, HIRAM, which was very successful at reproducing the tropical cyclone climatology. So this is a feature we would like to be able to keep in CM4. So we would have a climate model that can do climate change, but also look at tropical cyclone and how they evolve with climate change. This slide shows a snapshot of the tropical cyclone climatology in the CM4 prototype compared to observation. The top panels here show tropical cyclone location, and the bottom panels show a seasonal cycle for the northern hemisphere and mean number, and for the southern hemisphere. So overall, you see that the model does a fairly good job at representing both the distribution and the number of tropical cyclones. It probably underestimates a little bit the number, especially in the northern hemisphere, but this is quite encouraging. Another aspect of variability that we're interested in is the MJO, Madden-Julian oscillation, and those panels show the OLR-like correlation for the winter months, November through April. The first panel here shows the observations, and then the other 3 panels shows various models. So they're all couple models, and the main difference between those couple models is the treatment, the formulation of the convection. In HIRAM-like, we have a convection that is similar to what was in the original HIRAM model. In AM3-like, we have the convection as similar to what was in AM3, And this is the new prototype of CM4 that has the double plume convection from MingJa. And you can see that there's a dramatic improvement in MJO. In EM3, there was a little bit of an MJO, but extremely weak. In high-arm, it was almost non-existent. And now we have an MJO here that looks almost like the observation. This is quite an achievement that MingJa managed to do with his double plume convection. So we're hoping that this will able to, that we can maintain this improvement in the final version of CM4. Another area that I mentioned is undergoing revision and updates is the radiation. We have a new or updated water vapor shortwave continuum, and that has also a very large improvement. So this is a good illustration of where we improve the physical processes and we get a better simulation. So this is a very good illustration of what we're trying to do. In CM3, we had a negative bias in the amount of shortwave that is absorbed by the atmosphere, around 4 watts per square meter. So we were not absorbing enough shortwave in the atmosphere. And that bias has been almost entirely corrected with the new water vapor continuum here. You can see that the error map has much less color, much closer, and the RMS is much improved compared to CM4. This helps improve the precipitation, the global mean precipitation in CM4 compared to CM3. This is the last slide that shows some comparison between this prototype CM4 and other GFDL model and other simplified model. It's a very busy slide. I won't go into too many details, but basically what it shows is the column, I lost the mouse. Oh, there it is. The column shows various CMIP5 models, with the exception of this model here, which is our prototype CM4 model. And the rows shows various variables: geopotential height, wind, shortwave, long wave, surface pressure, temperature, and precipitation. And in each low rectangle, you have 4 triangles, which shows the normalized RMS, seasonal RMS, so DJF, MAM, JJA, and so on. So really what you're looking for is for blue colors, which indicate that the model is better than the ensemble. So you want, the better models are the models that have the most blue or the bluish colors in the entire column. So if you compare the gray area here, which is the prototype CM4, versus the green rectangle here, which is the previous generation GFDL model, you see that there's substantially more blue in this column than there was in this rectangle. So CM4 looks like it will be a substantial improvement compared to CM3, ESM2G, and 2M. It's also, if you compare to the rest of the model, it's also very encouraging. There's maybe not as good as some of the other models, but it's definitely looks like it may be in the top percentile of the compared to simplified models. So to summarize, AM4 and CM4 is starting to take shape. We are targeting a higher resolution compared to CM3 for both the atmosphere and the ocean. And at the same time, we are trying to increase the physical realism of the processes we are representing in the model. This is to improve, the goal for that is to improve the simulation fidelity, both in terms of mean, clouds, precipitation, WITCZ, and so on, and variability such as tropical cyclone and MJO. Now, when we do climate model development, nothing is really final until it is finalized. We often have surprises. We can hit unexpected problems. So the results I show are, I think, are positive and encouraging, but nothing is guaranteed until we actually finalize the model, which makes model development exciting, but sometimes more exciting than we would like. Thank you.
That's sobering. Thanks, Chris. Thanks, Chris. So let's see. If we have questions online, go ahead and raise your hand. Any questions in the room here for Chris? Just impressed by the MJO improvement and various other things. Yeah.
I got a question, Chris. This is Anarita. I'm wondering, you showed this persistent biases in the stratocumulus regions of the continent. And, we've had the vocals campaign. I'm wondering, how is that data being used during development, or is it useful, or anything you want to comment on how the process level observational data has helped this development for vocals or beyond?
So when we started working on stratocumulus many years ago, that was one of the initial starting point, was to develop a parameterization, and we were focused on vocals. So at that point, we did a lot of single column simulations, focusing particularly on the vocals region to develop improved cloud parameterization for stratocumulus.
Okay. So, Chris, I haven't seen any hands go up online. We have lazy digital hands today. I don't know what's going on. We'll have to get a lot of questions for Roger. Sorry, Roger. All right. Thanks a lot, Chris.
Thank you.
Let's see. Roger, are you there?
I'm here.
Okay, great. I'm going to transfer control over to your computer.
All right.
Looks good. Whenever you're ready, go ahead.
All right. So I was going to talk today a little bit about some work I've been doing on trying to implement an adaptive vertical grid into the model. So as I'm sure many of you are aware, there's been a lot of interest in higher resolution global models, either in the sense of a global cloud resolving model or an MMF or super parameterized model in which a two-dimensional cloud resolving or a small three-dimensional cloud resolving model is embedded into a traditional GCM. And these MMF simulations, while they are in some sense intended to capture, quote, cloud scale motions, they don't really do that in the boundary layer. And in fact, they don't have sufficient resolution to represent or capture boundary layer cloud motions. And in fact, they do a poor job of capturing low clouds overall, and I'll show a couple slides on that here in a moment. And so how are we going to solve this? And certainly going to a higher order closure or some kind of combination of a higher order closure with increased grid spacing has certainly shown some promise. But here I'm taking a somewhat different approach, which is I'm going to ask the question, can we get significant improvements by just adding a small number of vertical layers just where we need them, rather than trying to have a lot of vertical layers everywhere, or rather than going to some combination of a higher order closure. So in regard to the low cloud amount, I show here some results from original MMF runs done at 4-kilometer resolution, as was initially done by Krueger and Randall. And shown in the upper left-hand panel is the sort of cloud amount we see with the MISR sensor on board the NASA Terra satellite. And that upper right panel is what's produced by the MMF model, where here the low cloud fraction is determined using the MISR instrument simulator to make as close to an apples-to-apples comparison as we can. And as the two bottom panels show in terms of the zonal profile or the actual sort of global distribution, the model doesn't produce enough low cloud almost everywhere and is particularly poor in the stratocumulus regions. And to dig into that a little further, I show on this slide some actual histograms of cloud top height versus optical depth that are observed on the left and simulated on the right, here for the year 2001 using fixed sea surface temperature, so an AMIP style simulation. And you can see not only are in, say, the stratocumulus region as represented by the California area here, or off the coast of California, I should say, the model not only doesn't produce enough low clouds, but what it does produce at 4-kilometer resolution has been termed stratofogulus. It's a very, very low cloud deck, basically a fog deck on the surface. And in fact, when you try to increase the resolution of the model, what tends to happen is that a lot of this stratocumulus or stratofogulus actually evaporates. And you actually end up with even less cloud in these regions as you go to slightly higher MMF model runs. And we also see when we look at tracumulus regions as represented by the middle set of panels, You tend to do a little better in some sense with clouds, but they still tend to be too low and not physically thick enough for the most part. I should say physically thick in the statistical sense here. And I'm not going to talk about the tropical Western Pacific here today. So if we were to step back and ask the question, what kind of vertical resolution might we need to really model a stratocumulus cloud? And I show here one example from the Aztecs case. That's one of the GCS sort of standardized stratocumulus cases, where I look at running the model with varying amounts of horizontal resolution, where here the black curve is the highest vertical resolution at 12.5 meters and 128 vertical levels. And blue is not doing too bad at a vertical resolution of 25 meters, and green perhaps not too bad, and it gets considerably worse as you reduce the resolution. The simulation, the CRM, just can't maintain a cloud in this region at all. And so the details here vary significantly from case to case, but this is sort of a typical result. You find that as you get to sort of 25 to 10 meters, high resolution LES style or very high resolution CRM models tend to converge on a solution for that model at least. So these results suggest that we really would want something on the order of 25 to 10 meters in terms of horizontal resolution, vertical resolution to represent this. And then the question I guess I asked earlier is, can I represent this cloud with a small number of levels? And the answer is to some degree, yes. Shown here in the dotted line is that same simulation, but where I've actually, and I've only used 30 levels, but I've sort of cherry-picked these levels. I've put them just around cloud top and just around cloud base. And initially, this works out pretty well for the first hour and a half or so of the simulation. But then the things go south, and the simulation gets worse in some sense even than the 100-meter resolution run. And what's happened here is that the inversion height of the model has changed. It's gone up. And as a result of that, the picking the model levels at just the right place, while they were at just the right place initially, over time, they needed to be moved in order to sort of maintain a good fidelity simulation with a small number of layers. And so really, you can get a good simulation with a fairly small number of layers, but somehow we're going to have to adaptively move them. And I've come up with a couple different schemes to actually do this. And unfortunately, there's no simple or even any, for that matter, set of rules or equations that can tell us where we need levels or what the vertical resolution needs to be. If only that were the case, all our lives would be much easier. So I've come up with a number of different criteria to try to determine where to place these levels. For example, one can just look for putting levels right near the inversion, which is represented here by the green dashed line, where I'm looking at some criteria for trying to put layers where there's a large change in the potential temperature. Or I can look at some criteria where I look at the subgrid scale scheme and see how the subgrid scale to total water flux, vertical water flux compares. With the idea being that wherever the subgrid scheme is doing a lot of work, I really want to add some model layers and effectively represent or directly model that rather than letting the subgrid scale scheme take care of it. And by and large, depending on these criteria, you can get reasonably good simulations for both this Aztecs and a number of other GCS case studies, the details of which you can find in the paper listed here at the bottom. The lower panel here, by the way, I show the number of vertical levels for each 200 meters in the atmosphere, and you can see this sort of red shape moving up, and that's basically the adaptive scheme. Over time, it starts with a lot of layers here, but then as the inversion height moves up, the concentration of layers is moved, and some of the ones that were down here are no longer necessary, and so they're taken out. So what happens when we put this into the MMF? So in this figure, I show sort of the global low cloud cover. Again, the upper left here are the MISR observations. This for September 2000, and here two simulations. The one listed AZG0 is basically the MMF model run here with 250-meter horizontal grid spacing and 52 vertical layers, which give about 100 grid spacing in the boundary layer. And the one labeled AZG5 is the adaptive scheme, and it actually uses, this version 5 uses a combination of all three of those criteria that I mentioned on the last paper, and has actually been set to be quite aggressive in adding layers, but the maximum number of layers is capped to be 30 more than the original starting 52. So what you can see is that there's the low cloud, the total low cloud cover remains much below what's observed by MISR, and there is some improvement in the low cloud cover, probably best seen by these zonal plots here, in the adaptive grid version rather than the fixed grid version of the model. But the improvement is really quite modest compared to the total deficit of cloud. And when we look in more detail at what's going on, in fact, it's in the trade cumulus regions where we've seen the biggest improvement. So while my goal in most respects was to improve the simulations in the stratocumulus region, what's happened is that, in fact, the simulations have gotten better in the cumulus regions, and they haven't improved very much in the stratocumulus regions. So you can see here in this upper left panel, this is the distribution of cloud top heights, where the red is the original model, or the 52-layer model with fixed grids, where there tend to be too few and too low trade cumulus clouds, and they fill in quite nicely with the adaptive grid. And it also shows up here in terms of the distribution of cloud optical depths. The clouds are really filling in nicely, and the only pieces that we're missing are the really thin stuff, which in the observations are really cloud edges and subfilled cloud pixels. So this is a very nice result here in the top. But for the stratocumulus regions, as represented here by the stratocumulus off the South America, there's very little improvement in the model overall. So in summary, a cloud resolving model with an adaptive vertical grid has been added to the NCAR, in this case, CAM5 MMF model, and simulations with the AVG scheme show some modest increase in low clouds, but most of the improvements in cloud cover occur in the cloud amount and vertical structure occur in the cumulus-dominated regions rather than pseudocumulus. And so this raises the question, why is there so little improvement in the stratocumulus? I should comment that I've looked in detail at how the model's running, and it's doing what it's supposed to do. It's adding vertical layers where it should and when it should in these stratocumulus regions, but nonetheless, it's not forming significant amounts of cloud. And so one might posit a couple of different reasons why this is happening, and I don't know the answer, and I'm currently exploring that. My best hypothesis at this point is that what's going on is that there's a advection problem due to the vertical mismatch between the host model and the CRM. That's to say, while I'm adding vertical levels, those vertical levels are only being added in the cloud resolving model. They're not being added to the host model, which continues to run with 52 levels. And so advective tendencies are still on that coarser grid and still may contain some footprint of the coarser grid. So, for example, the situation may be that a thin layer in the CRM, which a cloud should be forming or is trying to form, sees an advective tendency that includes some warm, dry air because of the coarser resolution of the host grid, which ends up evaporating the cloud. But there are other possibilities. It may be that although I've increased the vertical resolution in these runs with the adaptive grid, I still haven't gotten to the point where I've increased it enough, and there's issues related to the radiative coupling. So I'm currently doing some work where I'm trying to ensure that the radiative calculations are done within the CRM rather than in the host model, and done sufficiently well as to get the cloud top radiant cooling accurately for thin, weak clouds. And also it occurs to me that the particular model involved here, SAM, the default advection scheme, MP data, is known to be too vertically diffusive. And so there's another option within SAM and the MMF that I've implemented in it to use the UM5 scheme, and I plan to do some runs to test that as well. So that is where I am in this project. Thank you.
Okay, thanks a lot, Roger. Appreciate the update. Any questions online for Roger? Again, raise your hand. Or questions or comments also from the other speakers, Chris or Steve, if you have anything to ask Roger, or maybe some comments on his results. Any questions here in the room? Okay, Roger, I'm not seeing anything pop up, but thanks for the update. Really appreciate it. Interesting update on your project. Okay, so thanks everyone for joining for the second February webinar. We're going to have a webinar coming up in March on Wednesday, March 18th from 2 to 3 p.m. This was rescheduled from what it said earlier on the website or on the One NOAA announcement if you get your information from those announcements. The topic of this webinar is modeling the stratosphere, and we're going to have a variety of talks related to stratospheric simulations and predictions, so discuss ozone and also reanalysis efforts and predictability and connections with the troposphere, some projects that are funded by the MAPP program. We're going to hear from Ming Kai from Florida State University, Judith Perlwitz from NOAA Israel, and Larry Horowitz from NOAA GFDL. So please come back on the 18th. And this particular webinar today will be archived on our website, and you can get the slides if you'd like to take a look at them again. So thanks everyone for joining. Thank you to our three speakers. Really appreciate you taking the time to present, and hopefully we'll see you all in March.